This lesson is over solving logarithmic equations. Recall the base exponential property. It stated if a raised to the power of x equals a raised to the power of y, then x equals y, as long as a is greater than 0 and a cannot equal 1. So example 1 says to solve. And for a, we have 5 raised to the power of x equals 125. Now, because we have 5 raised to a power, we want to, if possible, rewrite both sides of the equation such that they have the same base. Well, it turns out 125 is the same thing as 5 to the third. And since I have 5 raised to a power equals 5 raised to a power, it means since I have the same base, I only need to look at the exponents, which gives us x equals 3. And that would be your solution. Example B has 2 to the x power equals 33. Now again, rewrite using the same base. Since I have 2 raised to a power, can I rewrite 33 as 2 to some power? That's not possible. So what do? Well, that brings us to the property of log equality. It states log base a of m equals log base a of n. It's the same thing as m equals n. As long as m is greater than 0, n is greater than 0, the base a must be greater than 0, and a cannot equal 1. So let's see this in action. Example 2 says solve, state exact, and, if necessary, approximate answers to 3 decimal places. So let's look back at that problem. For a, we have 2 raised to the power of x equals 33. We know it's an equation and it has 2 sides, but I want to, if possible, rewrite using the same base. But we saw earlier that's not possible, so what do? We use the property of log equality, meaning we will take the log of both sides of the equation. On the left, I will take log of 2 raised to the power of x, and on the right side, I take the log of 33. Now that I've introduced log, I can use all the properties of logs on each side. That means the product property, quotient, power rule, all of those come into play because the word log is now involved. On the left side, log of 2 raised to the x power. Since I have an exponent, a power, that means I can use the power rule. The power rule means I move the exponent to directly in front. It now becomes the coefficient. So the left side is now x log of 2. On the right side, I just have log 33. There's no powers, there's no multiplication or division, so it will remain log of 33. Now this is an equation and we are trying to solve for x. So we need to isolate x. On the left side, I have x times some value. Well, how do you undo multiplication? You divide by whatever that value is. In this case, I will divide the left side by log of 2, as long as what you do to one side, you must do to the other side. And any number divided by itself will reduce, which gives you x by itself. And on the right side, log 33 over log 2 will remain just as you see it. Now, just a fair warning, this is not the quotient property. Log 33 divided by log 2 is not the same thing as log of 33 over 2. So please make note of that. Now, log 33 over log 2 is known as your exact answer. Now, the directions said to state the exact and approximate. So now we're going to find the approximate, which means you will need your calculator. So to type this in, you would type the numerator log 33, and you must close the parentheses around 33, divided by log 2, close the parentheses. Once you've typed it in, select enter, and you should get the same decimal value that I get. Now, the direction said to round to 3 decimal places, which would give us x as approximately 5.044. For b, we have e raised to the power of t equals 1,000. And again, this is an equation, so it has 2 sides to the problem. Now, since I have e raised to a power, I want to, if possible, rewrite both sides of the equation with the same base. Is that possible? No. Which means we are going to take the log, or in this case, because we started with an e, we are going to take the natural log of both sides. Which means I will take the ln of the left side and ln of the right side. Since we've introduced logs, including natural logs, it means we can now use the different properties. Product, quotient, power rules, anything of that nature now come into play. Now notice the left side. Natural log runs off of what base? Well, it runs off of base e. And so looking at the left side, notice that base of e means e to some power will give me the result of e to the t power. What would be that power? Well, that reduces completely to t. On the right side, natural log of 1,000, we can't use any of the product, quotient, or power rules, so that will remain the natural log of 1,000. Now notice, t is already by itself. We have solved it. So this is known as your exact answer. But we still need to find the approximate answer. So we will need to use our calculator. So we type in this case, we will hit the ln button, the natural log button, type in 1,000, close the parentheses, and then select enter. You should find the same following value as me. Again, we need to round to 3 decimal places, and we should find t is approximately 6.908. Notice we did have to round up in this particular problem. For c, we have 5 raised to the power of x plus 2 equals 4 raised to the power of 1 minus x. Now again, this is an equation, so it has a left side and a right side. And if possible, we want to rewrite using the same base. But we can't do that in this case, so we will take the log of both sides. I will take the log of the left side, as long as I also take the log of the right side. Since we've introduced logs, we can now use all the properties of logs. And we do this individually. On the left side, I have log of 5 raised to the power of x plus 2. Notice since I have a power or an exponent, I can use the power rule, which means the exponent now goes in front of the log and gives me x plus 2 times log of 5. Now, because your exponent involved 2 terms, you will need to have parentheses around x plus 2. We've looked at the left side, now it's time to look at the right side. On the right side, we have log of 4 raised to the power of 1 minus x. Since we have an exponent, we will also apply the power rule as well, which would give us the value 1 minus x, again in parentheses, times the original log 4. All right, so from here, what we want to do is we are going to distribute. On the left side, I have x times log 5 and 2 times log 5. I distributed the log 5 to both terms. On the right side, I need to do the same. I need to distribute the log 4 to the 1 and log 4 to the x. So I get log 4 minus x log 4. Now the ultimate goal is to solve for x, so we need to find our terms that include x's. Notice I have an x on the left side of the equation, and I have an x term on the right side of the equation. I need them to be on the same side. So I am going to choose to gather those terms on the left side of the equation, which would give me x log 5 plus x log 4. Next, I want to move all the terms that do not have an x to the right side of the equation, which would give me log 4 minus 2 log 5. So I've now gathered my x terms on the left side, but the problem is x is still in two different locations. I want it in one location. So on the left side, how many terms do you see? Well, we have 1 and 2. Notice both terms contain an x, which means I can factor out the x. If I factor out the x, that would leave me with two terms being log 5 plus log 4. And then everything on the right side remains the same. Now, we're still on a mission to solve for x. We're trying to isolate x. On the left side, I have x times something. So how do you undo multiplying by something? Well, you simply divide by whatever that something is. So divide the left side of the equation by log 5 plus log 4, as long as what you do to one side, you must do to the other side. On the left side, log 5 plus log 4 divided by itself will reduce, leaving the left side with just x. Now on the right side, you still have log 4 minus 2 log 5 all over log 5 plus log 4. This is known as your exact answer. But now we need to find the approximate, and you must be very careful on the calculator. So let's see how to type this in. Because in our fraction we have more than one value in the numerator, you will need to have parentheses. So it will be parentheses log 4 close parentheses minus 2 log 5 close parentheses close parentheses divided by. Now in the denominator, because you have more than one term, you need parentheses again. So in the bottom we have parentheses log 5 plus log 4 close parentheses close parentheses. Once you've typed that in, select enter, and you should get the same decimal value that I get. Now again, we need to round to 3 decimal places. So it will be negative 0.612. We do need to round up in this instance. Example 3, directions say to solve. And for A, we have e raised to the power of negative c equals 5 raised to the power of 2c. Again, if possible, I want to rewrite them with the same base. But e raised to a power is not the same thing as 5 raised to a power. So since it's not possible, we will take the log, or in this case, the natural log, since there was an e involved, on both sides. So on the left side, we take the natural log of e raised to the power of negative c. And on the right side, we take the natural log of 5 raised to the power of 2c. Since we've introduced log or natural log, we can use all the properties of logs, product, quotient, power rules, any of those come into play. Now notice the left side, natural log of e raised to the power of negative c. You have to remember, natural log runs off of base e, which really means e to some power gives me e to the negative c. Well, what does that reduce to? It reduces to the power of negative c. Now on the right side, since I have natural log of 5 raised to a power, that means I can use the power rule. So the exponent of 2c now becomes the coefficient, giving me 2c of natural log of 5. Now we're on a mission to solve for our variable, which in this case is the letter c. We need to get them on the same side. Notice I have c's on the left and on the right side. So I want to gather my c's on the right side of the equation, so I will add c to both sides. Now since I have two terms and they both contain a c, I do want to factor it out so it's in one location. When I factor out the c, that will leave me with those two terms of natural log of 5 plus 1. Because remember, when you're factoring, you are simply dividing. And so c divided by c leaves you with a 1. So you must have that placeholder there. Since we have c in one location, I want to solve for c. Notice that is c times some number. Well, how do I undo multiplying by some number? You divide. So to isolate it, I will divide the right side and the left side by that value of 2 natural log of 5 plus 1. And any number divided by itself reduces to 1, leaving you with c on the right side. And on the left side, 0 divided by any number is simply 0. So in this case, we do have our exact answer, and we do not need to find an approximate. Example B, we have 3e to the negative c power equals 12. Now this is an equation, so we draw our line. Now notice this problem looks a bit different. We do have an exponent, but we don't quite understand the base. So we cannot tell if the bases are the same because of the coefficient. So we must isolate the base. In order to do so, we need to divide the left side and the right side by the coefficient of 3. When we do that, that leaves us with e to the negative c equals 4. Now that we clearly see the bases, see if we can write them as the same base. Unfortunately, that's not possible, so we will need to take the natural log of both sides. The reason why we take the natural log and not the log is because there is an e involved. So we take the natural log of the left side and the right side, which now gives us natural log of e to the negative c equals natural log of 4. Since we have introduced natural log, we are now allowed to use properties of logs as long as we apply them fairly. Now notice natural log runs off of what base? Well, it runs off of base e. Now notice base e of e to the negative c power, that whole thing reduces to what value? Well, it reduces to the exponent, which in this case is negative c. On the right side, we still have natural log of 4. Now our ultimate goal is to solve for c. Unfortunately, we don't have c, we have negative c. So we need to isolate the variable. In order to do so, we need to divide the left side and the right side by negative 1. When we do that, we are left with c equals negative natural log of 4. This is going to be our exact answer. Now we want to know the approximate answer, so we will need to use our calculator. In the calculator, you will type negative natural log 4 and make sure you close the parentheses. Once you've typed that in, select enter, and you should find the same values as me. Now, in this case, we are going to assume to approximate to 4 decimal places, which would give us negative 1.3863. In this case, we will need to round the fourth value up. Now, we have looked at equations that begin with the exponents, but what happens if it starts out with a logarithm? How do we solve that? Well, when it comes to solving log equations, it depends on what the equation looks like. If one side of the equation has logs, then the first thing you will do is make sure to obtain a single log on that side by using the product, quotient, power rule, anything that you can, such that you only see log written one time on one side. Once you've done that, you rewrite the equation as an exponential equation. From there, you would solve the equation, and then we must check the validity. Remember, whatever your answer is, you have to plug it back into the original and make sure you're taking the log of a positive value. Now, that's if you have log on one side of the equation. What happens if you have log on both sides of the equation? Well, in that case, you would obtain a single log on both sides. So on the left side, I should only see a single log. On the right side, I should only see a single log. Once you've done that, then you will apply the property of log equality. In other words, you will have the ability to unlog an equation, as long as what you do to one side, you must do to the other. From there, you solve the equation, and then again, you have to check the validity. Once you have your answer, you must take it back to the original and make sure that you're taking the log of a positive value. Let's look at a few examples. Example 4 says to solve, and for a, we have log base 2 of x equals negative 3. Now again, this is an equation, so I draw my line at the equal sign. And now we look for clues. Does log appear on one side or both sides? Well, notice log is only on one side, so here's our steps. First, it says obtain a single log on that side. Lucky for us, the left side only has log appearing once, so we go to the next step, which is to rewrite as an exponential equation, which means we go back to what it really means to have a log. Our base is 2 raised to what power? Negative 3 equals what result? Equals x. There is your exponential equation. From here, we try to solve for x. Good news is x is already by itself, but 2 raised to the negative third really is what value? So since we have an exponent, we have to remember our exponential rules. Negative exponent means reciprocal, which means to flip it. So it becomes x equals 1 over 2 to the positive third. From here, notice 2 is in the denominator, and it will stay in the denominator, but we know 2 to the third power is 8. So in this case, x equals 1 over 8. So we have solved it, but before you draw a box around it, we have to check the validity. Remember, you cannot take a log of a negative number. So we must plug this value back into the original and make sure that it's a positive value. Log base 2 of 1 over 8. Is 1 over 8 a positive value? Yes, which means that is your solution. For b, we have log base 5 of 8 minus 7x equals 3. Again, this is an equation, so draw your line. And now we need to look. Do we have log on one side or both sides? In this case, we have log is on one side, so again, I have our steps. First, it says obtain a single log on that side. Lucky for us, on the left side, log only appears one time, so we're good. We move on to the next step. The next step says to rewrite as an exponential equation, which means we go back to what it really means to have a log. My base was 5, raised to what power? 3 equals what result? 8 minus 7x. This is your exponential equation. From here, we want to solve. Notice 5 to the third means 5 times 5 times 5, which we know is 125. So our equation is now 125 equals 8 minus 7x. We look at the equation. Is this linear or quadratic? Well, since we only see x, it is linear, which means we need to isolate x. To do so, we would subtract 8 on both sides, giving us 117 equals negative 7x. To isolate x, we need to divide both the right side and the left side by negative 7. That gives us x equals negative 117 over 7. This does not reduce. But before you put a box around it, we have to check the validity. You cannot take the log of a negative number. So if I go back to the original, log base 5 of 8 minus 7x. In place of x, I plug in our value of negative 117 over 7. Now notice, inside the parentheses, the grouping, we have to abide by order of operations, which means the multiplication comes first. Notice that's a negative 7 times a negative 117 over 7. But what's a negative times a negative? It's a positive, so the result is 8 plus 117. Would the result of that be positive? Yes, which means we can keep our answer. For C, we have log of x plus 5 minus log of x minus 3 equals log 2. Again, draw your line at the equal sign. And now we check, do we have log on one side or both sides? In this case, we have log on both sides. So our steps are a little bit different. First, it says obtain a single log on both sides. So looking on the left side, do I have log only appearing once? No, I actually have it twice. So this is where we apply the power rule, product rule, quotient rule. So first we look, do we have any coefficients on the left side? No, which means we're not using the power rule. Next we look between the logs. Do you see plus or do you see minus? Since it's a minus, that means that will be the quotient rule. Quotient rule means I will now write a single log, and then the first value will be the numerator, the second value will be the denominator. So we now rewrite it as log of x plus 5 over x minus 3. So we have simplified the left side to be a single log. On the right side of the equation, do we have a single log? Yes, so that will remain log 2. Since I have log of a single value equals log of a single value, we're now ready for the next step, which is to use the property of log equality. In other words, we unlog both sides of the equation, leaving us with x plus 5 over x minus 3 equals 2. This is our new equation. Now, since I have fractions, I do want to eliminate the fraction, and I can do that by multiplying the left side and the right side by whatever the common denominator is. In this case, our only denominator is x minus 3. So I will multiply the left side and the right side by the same value. The left side, the x minus 3's reduce, leaving you with x plus 5. On the right side, you will need to distribute the 2 to both terms, giving you 2x minus 6. From here, we want to decide, is this linear or quadratic? Since it's linear, we want to get the x's on the same side, and I'm going to choose to have the x's on the right side. So I subtract x. So I now have 5 equals x minus 6. To get x completely by itself, I need to add 6 to both sides, and I find x equals 11. Again, we're not done yet because we have to check the validity. In this case, we had log appearing multiple times, and we have to check all of them. So the first one was log of x plus 5, and I replaced x with the 11. Is 11 plus 5 a positive value? Yes. The second value we had was log of x minus 3. I replaced the x with the 11. Is 11 minus 3 positive? Yes. And then the last one was log 2. Notice there was no x, so there's no place to plug in, which means we can keep this solution. For D, we have log base 5 of x plus 4 plus log base 5 of x minus 4 equals 2. Again, this is an equation, so it has two sides. And we need to check, does log appear on one side or both sides? In this case, it appears on one side, so I have our steps on the screen. It says first obtain a single log on that side. So in this case, log appears on the left side, but it appears more than once. So first we look for coefficients. Notice neither of those have a coefficient, so no power rule. Next we look between the logs. Because we see addition or a plus, that means we will apply the product rule, which means we will multiply. So we keep log base 5 of x plus 4 times x minus 4 equals 2. Now x plus 4 times x minus 4 can be multiplied, and when you multiply those two binomials, you will get x squared minus 16. So we now have a single log on the left side in the form of log base 5 of x squared minus 16 equals 2. Now we're moving on to the next step, which is to write it as an exponential equation. Since we had a base of 5 raised to the power of 2 equals the result of x squared minus 16. Now 5 squared is something we can calculate. 5 squared is the same thing as 25. Now we're ready to solve this equation. Is this linear or is this quadratic? Because it's x squared, it is quadratic, but notice there's only x squared. There is no x term, which means x only appears in one location, and I want it to get it by itself. So to get x squared by itself, I need to add 16 to both sides. When you do, you get x squared equals 41. Now notice, I don't have x, I have x squared. So how do you undo squaring something? Well, you take the square root of both sides, but don't forget about the plus or minus. And so the square root of x squared leaves you with x, and 41 cannot factor. But we have to separate our answers. We have two separate answers. We have the positive version of x equals square root 41, and we have the negative version, x equals negative square root 41. So these are our exact answers, but we have to check our validity. And to do that, we need to know approximately what is the square root of 41. If you type the square root of 41 in your calculator, you will find it's approximately 6.4. So now let's check our answers. For the first value, log base 5 of x plus 4, if I plug in the first value of 6.4 in for x, I just want to make sure the value I'm taking is a positive. 6.4 plus 4 is positive. If I plug that same value into the other log, this time I get 6.4 minus 4. Is that still positive? Yes, which means I can keep that solution. Now we must check the negative version. Log base 5 of negative 6.4 plus 4. Is that positive? No. What about the other value? Log base 5 of negative 6.4 minus 4. Is that positive? No, which means we cannot keep that solution.